Hi, I'm Timothee Verdier. I'm going to give a talk called Hands-on Neural Network for Natural Language Processing. Okay, so while you are downloading, I might as well do the introduction. So, so we don't lose time because we are on a very tight schedule with all the material we have here. So welcome everyone to this workshop about application of neural networks to natural language processing. Natural language processing is obviously a pretext to get familiar with neural networks, with evaluation of the neural network, usage of the neural networks, and basically what we're going to see today can be used on anything that is sequence-based. So it can work also for signals like audio, text, which is the main basis for natural language processing. For you might have video, sequence of images, and so on and so on and so on. Right? It's going to be both a primer on neural network because we're going to start with the basics, evaluation, training, and so on, and a very advanced course on network architecture. And so the way we're going to do that is by following a rocket launch path. Okay, so if I don't have any interruption, any question, I would probably give more and more momentum to the presentation so that we go as far as possible, which is probably the best way for you not to ever come back home with all your parts. So you're very welcome to interrupt me, to ask questions, to try things, and to make this workshop a real workshop instead of just listening to the talk, which is not what this is meant to be. And also because it's natural language, just quick reminder about it. If you ask me what natural language is, I would answer it's French. But you might ask a question in English also. And I'll do my best to, well, process in English. So that's it. And I will try to leave the URL a bit, but we need to move on. Okay, so first, natural question to ask to start with the workshop. I'm starting assuming that the audience is very broad in knowledge about neural networks and so on. So first question is probably what's a neural network? Scholar answer would be basically it's a differential transformation on ND array that give you the idea. The way I explain my work to my friends so I keep friends is basically it's a transformation. It takes a blah and it makes another thing out of it, and it has some buttons that you can gently, smoothly move in order to tune the transformation. And you can move the position, and therefore you can seek a good transformation by playing hotter and colder, warmer, and trying to get to a soft spot. Right. So and that's done for the yes. You should run. It should run on any version of Mathematica which are official. But if you have the beta release of the version 12, that should be given to you for this tech conference. That's the one I'm 100% sure it completely works on because I bulletproofed it. Well, at least on the Mac, at least on this Mac. Okay, so quick tour about what we're going to do. Start with the foundation. So we're going to just get a neural network model and see what it's like, evaluate it, and move to the anatomy dissection room try to take apart the components, see what they look like, and dismember the neural network, reassemble it, and then from these bricks, we're going to see we can build houses, which is several different architecture of neural network. Those houses are like modules you can assemble to get cities, and so on and so on and so on, right? And we will focus on a family of those transformations which are a sequence type of structure. But once you have the understanding of how this works, you could basically navigate for any type of application, right? So let's start. First thing you need to do is to evaluate the first line. That's the only time I will tell you how to evaluate a cell, which is shift answer on the shell. You just kindly answer no to any question this stuff asks, and you get your neural network. Right. So I'm now using the material notebook you should all have. And what we are downloading here, I'm not going to say much about the neural network repository, but just know that there is there's probably a talk about it already or to come, but there is a huge library of network models and architecture you can download and use directly. They are open sourced on the internet. You can get them and do whatever you want with them. You can even export them to other formats and get away with them, right? So if you're inside the notebook, if you have Mathematica engine running, then you can use the net model function. And you only need to know what you're looking for, which is the name of your model. And if you don't know the name of your model, you can browse the website. That's all. So here is the first model I'll introduce you to, which is this network. So basically, basic one, you just see it looks like a stacked ensemble of what seems to be called layers with various names. And so we have an input, an entry, and we have an output. So first things to do, once we have a network, which is now called net, is to try to evaluate it on something. And since I'm on Mathematica, I'm evaluating on this symbolic formula. And this symbolic formula is something that the network cannot swallow. So it's going to yell at me, just saying that this is an invalid input, because input was not a string. So this network wants a string, and let's provide it with a string. And you see it just output a new string as a single character. So basically, this network is a language model. Means it was trained on a sequence of characters to predict the most likely next character, or the likelihood of the possible next character, right? So you give it a string. It assumes it's a context string. It says, given this context, what's going to follow, OK? You can also batch evaluate, that is, evaluate in parallel the network on several inputs. So this is what, which is the most likely string given wa. And if you evaluate on wa, we, where, we, whatever, you got what, when, and which is the best guess that the network can give you. And why do I show you the batch evaluation? It's because one of the very powerful features of the neural network is that they are heavily parallelizable. It means that you can parallelize the computation, and you're going to get a lot of speed improvement. Just to show you, we're going to just get an example data, which is the text of Alice in Wonderland, right? I'm not showing it because it's going to blow the notebook. And there is this function here that I've written for you. What it does, it simply pick random location in the text and extract a snippet of 10 characters. That's basic things that we can feed the network with in order to get the next character, right? So test data would be some random snippet extraction in the text of, and let's take 500 of them. We can look at what it's like, right? It's a snippet of the text in Alice in the Wonderland. And we can submit them in two different manners to the network. First one is mapping, that is sequentially passing the string to the network, or batching, that is giving all the strings at once. right? And which we should obtain the same result. So it's same queue of the map and the batch, right? So true says it's exactly the same thing, whether we pass it sequentially or as a batch. And but you can see the timing here looks like we have at least a factor 6 in terms of computation, right? So if you came with your computer and if you manage to download and follow me up to here, you have evaluated maybe your first mathematical network, or maybe you just evaluated a network. That's and that enables us to move to the next step, which is try to go and make some surgery on this network, because it's what networks are interesting at. It's to be cut apart and to be reassembled. Like it's really Lego transformation. So as this network is a chain, what we're going to do is we're going to extract first part of the network, then one step further, and so on and so on and so on, and we will follow the flow of the information at each step, the way they are processed, right? So first, I told you neural networks, that's something that work on numerical ND array, so like big bunch of numbers, and strings, they are not officially numbers. So this neural network and neural network in Mathematica are not pure neural network. They have something called net encoder at the input, could be there, which is an interpreter, if you like, which is going to translate the input into the numeric world. And so this net encoder is expecting some character and is returning a vector, so a sequence of n indices between 1 and 97. So this net encoder knows 97 characters, and for each character, will generate a number, right? Very basic. Each character has its indices. You can get rid of this pre-processing step, getting rid of the net encoder, but replacing the input part of the network and putting automatic, which is the network is now expecting numbers, right? So RowNet will now yell if I give him a string, if I give it a string. Okay, so first part of the network is just generating a list of indices for each character in the string. No, this is not a very rich encoding, right? Basically, being two characters next to one another doesn't tell us much about whether we are similar. Like there is no real reason for A be next to B and far from C or from O, I think. But so what we can do is to take this information and move it in another space that is richer, and that's the second step. If we extract the first stage of the actual network, which is what I'm doing here, I'm saying take inside the net, which is a stack of layers, a chain of layers, take inside the net up to the layer 1. And I get a new net chain, so a new stack of layers, which goes from input to the first part, and then the output is just whatever is processed. And I can look at what the result of using this beheaded net on the data on larger and larger string. So W gets transformed by the pre-processing to 90, and 90 gets transformed to a vector. So this first stage of the network is called an embedding. What it does, it just picks the numbers, the index, and do a lookup inside a table of vector, saying, oh, 90, here's your vector. Why do I want to do that? Because vectors are much richer in terms of the vector space is much richer on what I can encode than just the number, right? And therefore, I can use those vectors to encode some semantic of my problem. And that's all embeddings are about. Because those numbers, those vectors, they're going to be learned, okay? And what does it, yes?
Can you talk a little more about that? Like, how does
Yes, yes. So I don't know which screen you prefer, but basically the first part, the pre-processing, just outputs the integer of the first character, that is 90 for W, and this first layer has just a table of vector and gonna pick the 90th vector.
Is it always the same for all neural nets?
No. No, this lookup table is basically a table of random vector, which values have been tuned during the learning phase of the network. So this table was tuned in order to have some semantic inside the vector direction, if you want, that will help the vector to solve the task. That is, given those characters, what is the next that is coming? Okay, so I'm going to show you an example that is maybe more easy to understand. So indeed, if I get rid of the pre-processing step, I can just pass the values of the index and make the lookup in the table, and you see that indeed the first vector, that is vector number 90, is always the same, and I'm just going from a sequence of integer of index to a sequence of vector. Why do I want to do that? This is something, if you have patience or if you came in time to download Glove, which is a very well-known embedding. It's something that I can show you. So Glove was trained not for an embedding on characters, but on words level. That is, each word gets a number. So I have a vocabulary, let's call it a dictionary. It says, boat, number 25. Then Glove is number 25, boat, what do I get? And it will give me a vector. And it was trained on a task to predict next work, or to predict, actually Glove was trained to predict how clause works, whether I can substitute one word for another in a sentence. So the idea is that similar vector in terms of direction should have similar meaning, right? Directions is direction on a sphere. On the ND sphere, it's like a 50-dimensional sphere. And so the distance is a cosine distance. You take the angle, you look how big is the angle. 0 is very close, it's the same. And then it goes to 1 or 2, depending on what you divided by p or 2 pi or whatever. So let's try it. So evaluate the word distance and try the word distance that is just taking the vectors and computing the cosine distance between them. And what it said that sheep and boat, or sheep, I don't know, one of the two, are close together, right? 0.1 is quite close. So they share some semantic. That boat and carrot doesn't have a lot to do together, but that carrot and zucchini are somewhat related in the order of magnitude that boat and sheep are, right? Yes?
What's the size of the vector that the word has?
Yeah, it's Glove 50-dimensional, saying that you get a vector of size 50. And also, the bigger your space, the more information you can encode. But tests on that showed that there is a soft spot. For most of the embeddings that people have been training, you're somewhat between 50 and 300 seems to be the right values. And then depending on how heavy you want your network to be, how fast you want it to be computed, you will pick one of those. Sorry? It's the paper read were saying that between 50 and 300, it's somewhat the good spot. But this was for natural language and for this specific task, that is similarity between words, right? So we have this list of vectors, and if we have an embedding that was previously trained, we have some semantic. But we might also have an embedding that is just random, blank from start, and we will train it later. So we have a sequence of vector, and now we're going to process them. And given the fact that we are focused on sequence here, I'm going to introduce you to the next stage. So let's take network 1 to 2. And well, actually, let's see what stage 2 is doing. It's called Dropout Layer. And basically, this is a idle guy that is doing nothing, right? So if you take the first step and you step up to the second layer, it's exactly the same thing. So let's forget about this guy. Maybe we come back later, maybe not. It's something we're not very interested in at the moment. It's not doing anything at evaluation. So let's take up to the third stage. Here is the new net. Input, embedding layer, dropout layer, we forgot about its identity, and gated recurrent layer. Recurrent layer. So recurrent layer is a family of layer. What they are doing is taking a sequence and generating a sequence. So processing a sequence. And why they are called recurrent is because they are using a recurrence relation. That is, they're maintaining a backward loop that is feeding back a state, some information about the previous computations inside the next computation, right? So it's an object that maintains a state of what happened and use it in the next. And then you have a large family of them, and we're going to use this gated recurrent layer as a representative of the family. You can basically use any others. It will be somewhat close in terms of results. So that's the idea. You have your sequence. You send your sequence vector per vector inside your layer. Your layer do some computation, generate a new vector, and this new vector, or some part of the computation, is fed back into the layer for the next computation. So we have this memory of what happened, okay? And we can look at what's going on. So we had three vector after the embedding. We still have 3 vector. They might be of different size. You know, the embedding was size 97. This embedding was of size 97 inside this network, and the gated recurrent network is generating vector of size 512. Okay. So there are some matrix multiplication, and you have an input which is 97 and an output which is 512. Right. So just a quick overview of how those gated recurrent layer work. It's very simple. We have this with netports input. We have a netport that is the initial state. So the first value we're going to feed to start the recurrence. And then we just feed back the output of the network as the next state, right? So we are being a recurrent layer, you will provide me one vector and an initial state, which is 0 if you don't say anything. I will do some computation and give you a new vector. I will also keep a copy of it. So if you give me a second vector, I will use it as a state to compute the third one, the second one, and give it to you. And keep a copy for the third one, and so on, and so on, and so on. That's very simple. You can code your own layer if you want. So let's have a basic graph. This is your first graph. We will generate a graph having a single recurrent layer, which is actually the third layer of the net we use. We're going to just extract the third layer, and we're going to input. We're going to use one entry for this network, which is netport input, which is called input, and which will be fed to the recurrent layer. And we will use another entry, which is called initial state, which will be fed to the entry state of the recurrent layer. Easy. So you get a net graph, says, I have 2 entries, 2 ports, initial state and input, and I'm giving you something on the port's output. And then we will evaluate this graph, which is a single layer, on the input first step net of W, so the embedding of W, and feeding a constant array of 0 as initial state. Okay? Just to show you what's going on, we get a new vector. Now, if you're not familiar with, I introduced you to fold lists. what for list is doing is just generating a recursive evaluation. So for list of x and a list is just giving you x, then f of x and a, and then f of f the x and a and b, and so on over the list. So, and that's exactly what the recurrent layer is doing. So if I do for list of this object, and since it outputs a sequence of size 1, I can just take the element, and feeding back this element over again as initial state. So I'm feeding back, I'm re-initializing the network over and over again with its output. I'm just getting exactly the same as the network produce, right? CQFD. So now, so this is a basic processing unit for sequence. Now, if I want to process more in order to enrich my transformation and have a somewhat richer family of transformation, I can stack them. So that's what the network is actually made of. It's 3 stacked recurrent layer together, right? So let's extract the network, and just so you cannot treat me being a liar, here you have your 3 gated recurrent layer. And then each layer is doing the same, taking the output of the one before him and doing this recursive evaluation with its own state and generating a sequence. So the size of the sequence is not changing at all. Okay? I see that you are super impressed. Okay, so the task is from a sequence to a single prediction. So in order to generate a single output, we will choose a representative of the sequence. And because it's arbitrary for me, and because there is some processing going on over the sequence with the recursion, a good choice seems to take the last one. I'm processing the sequence. The last element as seen, as it was computed with a state that takes as memory of all that happened before. Let's take it as the encoding of the sequence, right? So next layer, not very interesting. Let's just look at this guy. It's called sequenceless layer, and it's doing exactly what it's called. You look at the sequence, it just takes the last one. Right? And after that, so I have this layer of size 512, which is a representative of my sequence, and I want to generate a prediction over something that is size 97, because it's a number of characters I want to describe, right? What I'm going to predict is the probability for each character to follow what I've seen. 97 character, discrete probability distribution over 97 character, right? So let's make a linear combination of all the information that are inside this representative of the sequence and generate something that is size 97. Okay? That's a projection of the information I have that I will learn. I will learn how to project this information into something that I want to interpret as being probability distribution. So linear layer, it's purely a matrix multiplication with weight of the matrix being learned. Let's see that. Boom. So gated sequence-less linear layer. If I look, I can click on each layer and have information about it. It's telling me that I have, oh, that's impressive, a matrix of size 97 times 512. So those are the number of weights. Each weight is used to do the projection. It's simply a matrix. But if I want to interpret this projection as being an actual distribution of probability, I need to normalize it. And the standard normalization is the so-called softmax normalization, right? It's taking it's making sure everyone is positive by taking the exponential, and it's normalizing over the sum. And if you've done some physics, it's somewhat something you have seen about the energy and so on. You have the exponential of minus something over the sum of this. And this is a very interesting object that is doing some great thing. That is the reason why everybody loves it. So that's the softmax layer, right? It takes a vector and generates a probability distribution for each element of the vector being a probability, and everything sums to 1. So we now have the full neural network, and we have seen in detail by just taking apart, and now you know how to do some surgery on the network, take some parts, extract some part, and so on. And we now see what's going on there. We are just generating a number with this net encoder. Those numbers do some lookup operation in a table that generates a sequence of vectors. Those vectors are processed 3 times by a recursion with some computation with learned parameters. Then the output of this, only the last part is selected and projected in a different space of the appropriate size, and then it's normalized to get a distribution. And what I want is tuning all the weights in this guy in order to get that does this transformation actually fit and match the distribution of probability. So learn fit the distribution of probability of the characters. Last thing, as you can pre-process the input, you can also post-process the output depending on your needs. So a layer has a net decoder attached to it, which is taking this probability distribution, which is the thing you actually learning, and generating information depending on what you ask, properties. So you can say net of WHA, but this time I want the top probabilities, and I want 3 of them. And it says, OK, I gave you T as a prediction because it has probability 97%, but there is also 1.7% of probability being L, because it's not only what, it's also whales and things like that, right? And you can also say, well, maybe this network is a bit too confident. So I will change the temperature, which is basically a multiplicative factor inside the exponential. Very great physical meaning still. I will tune this temperature, so multiply everything in this vector here before I do the softmax, so that the probability, which are first in the log space, they became closer or further apart by this multiplication. So this making the distribution smoother, flatter, or more peaked. And so high temperature is something where everyone is a bit the same, and low temperature is something in which only the best choice is selected. All the rest is going to 0, right? And so exercise that I will leave to you, and you have the solution here because we need to move on, is evaluate cell. Here. How do you generate a sentence recursively using the language model, saying like, pick the next character, choose a character, sample from the distribution, and so on and so on. And you have this finished sentence here that generates a sequence of character with a temperature of 1 up to 100. And character by character, starting by WH, it generates something that looks like English, right? So who works for the start and then wondered why she was. I stopped at 100. I can change the temperature and says, for instance, temperature of 3. So it stops every time there is some return of things. With a temperature of 3, I have a lot of punctuation and things that I haven't accept or sentence. So it's fairly random, right? The generation. So it will stop quite soon or generate some crap. And with the temperature of 0.1, for instance, it will just just pick the best likely character, and so you will see patterns again and again and again.
Is temperature only in 12?
Sorry?
Is temperature only supported in 12?
No, that's something that I've hand-coded, and that it's really easy to just multiply here before you do the evaluation. So you just take out the softmax, do your multiplication, and normalize by hand. So it's supported since 11.1. Like first, sure. So probably I use a trick that is 12, but the idea is the same. And something that you may think is, how do I generate the next character? By feeding again and again the sequence that grows, right? And so every time the network is recomputing the whole sequence and moving on, and the sequence grows and grows and grows, and this is a lot of computation for things I already know, because I've already done the first steps. So one good idea would be, as a second exercise, and this is something that is new in 11.3 and in 12, the second exercise would be keep the state, keep it, and just feed the next character. So you just loop the next character, and you save the state inside your recursive network so that you generate only character per character very fast, right? And this is the finished sentence too. Last one, which is also an interesting one, is given the fact that I can just compute the probability of the next character, I can compute the probability of a word inside a string, right? It's just the product of the probability for each characters. And therefore, I can compute the probability of putting a word inside some context, left and right. And this is here. It says that I am very tired of working, as is somewhat 10 to the minus 7. It's not normalized, but that's, you can compare one-to-one the probabilities. That probability of being happy of working is less probable. That's in terms of what the network has met and learned. The probability of being very banana of working is somewhat to the minus 15, and the probability of being very valuable of working is 10 to the minus 25. So you can see and you can have a way to actually say, oh, this word may be an error, and things like that, right? Okay, so let's move on to training. So very small data set, movie review of data, and we're going to use a very similar architecture to classify sentences. So you have a movie review saying, oh, I've gone see this movie, and it was really, really bad. And you have to say automatically, depending on the sequence of character, whether this is positive or not. And you have a data set for that. So here are a few examples. Futile scenario, negative. You're not merely watching history, you're engulfed by it, positive. You have to be English speaker. Yeah. Once folks started hanging out at the barber shop, they never wanted to leave. Chance I won't either. Well, anyway, that's the data set. Okay? So I have examples like this, and I want the network to do that for me automatically based on the example. I want to learn this probability distribution. So it's a probability distribution. Instead of having characters, like 97 possibility, I just classify with 2 outcomes. And I want the probability of the sequence to be positive or negative. And I'm training it directly on those examples. So same thing. I take the character. I generate a lookup table, which starts random and then will be tuned. And from this lookup table, I'm moving into a recurrent layer. I'm just putting 1, just to see where it leads us, and then taking the last element of the sequence after processing as a representative of the sentence, projecting it in a vector of size 2, and normalizing it. Okay? Easy. First, this encoding stage, which is basically all this way up to the single vector here as a representative, encoding the sentence. So, and then decoding is probably not the right word here, but it's classifying. I take this representant of the sentence, and I'm making a decision, an educated guess, or at least I'm estimating its value. right? So two nets, which are just net chains. That is, I stack those layers together, and I put an encoder at the beginning. And and this encoder is encoder token. That is, I'm not taking just the character, but I'm taking words for the lookup table. Okay? So I'm training my own little glove. And you see that the vector will be of size 40, and gated recurrent will output size 32, and this is completely arbitrary. That's because I like it, and that's because it worked somehow. Okay? And then the sentiment net is that the encoding following by the classify, right? Here we have. And it's great saying like some weights are not set yet, and there will be affected random value at the training time. So let's train. How do I train? I give the network to net train. I give training data, which is just a list of rules saying this is positive, this is negative, and so on, and so on, and so on. And I want all the output of net train. And I'm putting some validation data, which is data I'm not providing to the network at the training time. Being the teacher of the network, I keep some exercise for the test, right? I'm feeding the network with exercise, it's trying to learn, and then I can validate that he learned something. Okay? And let's look at what's going on there. So the network is training. In orange, you have the curves of the validation, so the objective is getting warmer or colder, and blue is the actual value on the testing data. So you see that it's basically learning the sentence by heart, so it can be really good at classifying. You see the error is close to 0 on the sentence that is already seen, but is like more like 20% of what is on new object. So it's really important to have this validation in your data set so you can compare. But without doing nothing but providing the architecture, I have a network which has learned to be 97% good, accurate on the training set, and 76% correct on just putting the number of stars on the video benchmark based on the text you given it, right? Random one would have been 50% because there is two solutions. So he learned something, okay? And we can try, and that's where the dropout layer we seen together, that's a layer that is effective only at training. We can try to shake the data by putting random value to 0 so that each data we provide is a bit different from the usual data, and it's harder to learn by heart. So he has to find a more meaningful and generalizable transformation. So that's the main idea of dropout layer, is putting some variance on the data so that the network has a harder time at just learning by heart the data set. So just putting a dropout of 0.3 is saying 30% of the value of the vector will be randomly set to 0. And move on with that, but only at training time. And same network, just adding a layer. And the idea would be for it to follow it a bit further, a bit more, the actual training. But it's not a bulletproof solution. So if your data, if you have very small data set like this, I have just a few thousands of examples, maybe 10,000, that I have split in training and testing, shaking the data won't be enough. So you need more data in order to get better performance. Okay? But that's the idea of dropout, and all those that make sure that the network is learning something that generalize are called regularization system. Okay, so we can stop here. We see that it's going nowhere in terms of, it's still learning, but learning more and more by heart. So we stop, and we can see maybe we generalized a bit better. We've got 80% instead of 76, right? So, or what I can do is saying like, oh, you have too much degrees of freedom inside the embedding. The local table, you can store all the information there, so I can freeze it at training. Say, let's use this 25-dimensional vector, but you don't touch it, and I use vectors that have been learned on a different task with a much bigger data set. That's called transfer learning, and that's very efficient for small tasks, right? So do the same, replace my embedding by an embedding that I will throw that training. How do I do that? I do that by net train, learning rate multiplier. The first element in my network, which is in the encoder, the first layer, so 1, 1, as a learning rate multiplier of none, saying I'm not learning there, okay? And I can do that also, and I will have another training with a different curve, and possibly because I have less degrees of freedom, I will less overfit, right? But you see that the training is slower, but eventually, if I wait for those 3 minutes, I would get better results. Okay? I won't wait. So now let's move on to more interesting tasks. So this was binary classification. I take a sequence, I look for a probability of decision. But more interestingly are question answering. So I've got two sequences. One sequence is the context, and the next sequence is a question about the context. So I'm downloading this, if I can, I've downloaded this baby question answering data set, which is something like, oh, Mary is in the kitchen. Mary moved to the cupboard. Mary exits the cupboard and moved to another room. Where's Mary? And sometimes you say, oh, by the way, Mark arrived at the place. Some random information. I provide that to the network. I provide the question. I want the question to say Mary is in the kitchen. So the idea is that I have a problem with the sequence. I will choose a representative. So basically what I'm going to do is sequence last layer on the encoding of the question, encoding it's question and question. So, OK, encoding the context, encoding the question, taking a representative for them all, stacking them together. So this is the context and the question, and doing the classification. So you see that's very similar, right? So same thing. You should be able, as an exercise, to generate the question answer in net and training on the data, right? So this time, and this is, so we can follow a bit what's going on there. So you see that that's good because the validation is following the actual training accuracy, and so this is a loss. This is a prediction on the probability distribution, and then there was like picking the best guess. And if we look at the accuracy this time, just by counting the actual good answer of the network, we see that for something like, why does this? So typical context, Mary went back to the bedroom, Mary traveled to the bathroom, and so on. Where is Daniel? And Daniel is in the kitchen, right? So you see that I can predict over 1, 2, 3, 4, 6 different solutions, and I get one time out of 2, I got the correct one. I can try to improve this by changing the architecture to something more powerful, which is maybe one vector to encode the context is too small. And since I'm not overfitting, let's have a stronger architecture. That is, I encode the question is one vector, but I'm going to keep the full sequence as for the context. I'm going to stack them together, and then I'm going to process this sequence to generate a representative of the answer. Make sense? OK, so same network, generating some classification, and I train. So this time, same type of network, but I keep the whole sequence, and I'm going to just stack the question or representative over each word of the context, and this will maybe help the system to figure out in an easier way the answer, right? And And the learning goes, and that's a good learning because actually, that was a good learning because actually, but didn't get me much. So next idea is to see actually this encoding of the context should depend on the question. Because depending on the question I'm asking, I should look at different parts of the context. And this is a new layer that I'm introducing here, which is called the attention layer. And what it does, it takes each, so it generates some values and some keys for the context. And what it's going to do is that the keys are representative of the elements in the context regarding the queries. And for each element in the query, I'm going to look at all elements in the context and look for the one that is the closest in terms of similarity. So if the question is about Mary, it will match where Mary appears in the context, somehow. And then, out of those similarity, I will generate a list of weights saying I want to pay more attention at this part of the context. And this is a softmax over just the dot product of the query times the keys. And I will multiply the values by the saying like, this is this element I want to look at, this mixture of elements of the context, right? And then, process as usual, take the output of this mixture, stack the question on top of it, generate this sequence, a recurrent, which is now decoding, recurrent, last layer, and classification. So. So training again, and what we see here is that instead of those, with this attention, instead of those 96% of, basically going down to 0, which is that the network is, like, if the network is able to span attention over the context, is able to solve perfectly the task. That is, on that, if we look at the accuracy, so let's stop the training. Yeah, if we look at the accuracy, that's on the test data, the data it's never seen, it's 100%. That is that this task is definitely it can be fitted perfectly, right? Even on new data points. So attention is somewhat a great help for the. And now, because we have a few time left, let's move to a new type of task. So this is a great family of tasks, which is, you see, with 3 lines of code, just stacking some transformation together, providing some strings, and like a question string and a sequence of context, you get an automated answer of where is Mary. And so that classification is one very great family of tasks for sequence, sentiment analysis, all the comments on the web are rated this way because there are too many for human curator, right? Now what we want to be able to do sometimes is to actually generate a sentence. So that is like, you ask a question, I want the answer, or you want to translate. Translation is, I have a sequence of words in a language, and I want a sequence of words in a different language, right? So one toy example of translation, which I can show you here, it's to generate, given a list of integers, a list of strings that are integers. Okay, probably this is going to be the next example, but if you're not satellised, that's probably a lot of things to digest. So if you have a list of strings that are just 80941, let's take another one. It would be maybe Command D. So I'm gonna give you four string of integers, and I want you to translate that saying, sorting the integer in order, saying like I have 1 0 and 1 1 and 2 8 and 1 9. That's a translation, right? you're moving from a sequence to a new sequence, which is basically saying the same thing in a different world, in a different manner. So going to do that, and one way to do that is to actually take the representative of the encoding of the sequence, of the first sequence, embedding, recurrent layer, representative of the sequence, and use it as a state for another recurrent layer, which will be given the next character every time. So it should generate, right? It says like, OK, first word is 1. Then I will give you, OK, here is the state. Here is the first one. What's the next word in the sentence? And therefore, will generate a new sequence. OK? And so the way I will train is given the input. I have the input sequence, which is 72112. I have the target in the example. We start with the beginning of the target, then the correct answer, then end of the answer. And then the network will be provided this sequence. And this is how it's going to happen. I'm going to provide the encoding for 72112. And this encoding, it will try to decode it by generating a sequence. And we say, OK, first element is start of sequence. It would say, OK, my answer is 2. Right. I take this 2, and I feed it back to the network. Or actually, I take the next element. So instead of feeding back the answer of the network, I feed it back the correct answer. Right? So I take the next element, I feed it to the network. It said, oh, my answer is on. The correct answer was actually end. The correct answer was actually 1. I feed back the correct answer 1 to the network, and it said, my answer is still end. It's a bad network. But that was the correct one. And so on, and so on, and so on. Until I reach the end of the sequence, and then we will compare the answer of the network with the correct answer and give a feedback to the network. That's called teacher forcing. I provide every time I correct the network by putting it back on the track, and I try to generate sequence this way. And if you want to see the training, that's here, and we're going to stop there. You feel free to carry on with a notebook. But on this translation task, you see that the network, after that 1 minute of training, is already good at only this 6% error rate. So the network is able to translate from this 1, 2, 3, blah, 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 to the sorted order in natural language. And by replacing this by Japanese character and the correct output, you can do exactly the same to do automated translation, right? So let's stop it here. And now to generate the result, instead of, we don't have the right answer anymore, so we will just feed back the answer of the network at each step. So make your best guess, use the best guess to do the next, and so on, step by step. OK? And this is called greedy decoding because I only keep the best guess, but I could explore more in time. For every time if I've got 9 words in my vocabulary, the next step, I have 9 possibilities. Then there's 9 for each then, and it grows exponentially. So I have to choose one way to explore this tree and pick the probability in those objects. So greedy decoding, let's see what the network has. This is the encoding of the sequence. I have to take the decoding part of the net as an independent net to feed back the encoding and generate from it, right? So I evaluate the encoding independently of the decoding, and I generate. I will use inside this decoder, in order to feed the next element over and over, I will use the trick of keeping the weight of my network. So I will use a net state object that maintains the weight after one evaluation and make it ready to be fed with the next example. And now I can start to greedy decode the string 13342. And he said, I have 1, 1, I have 2, 2, which is obviously wrong, and 2, 3, which is good, and 1, 8, right? And if I change, if I change the if I train it longer, or if I train it with a different architecture, which I was going to show you, which is the architecture with attention too. With attention, you will reach 100% accuracy on this task, right? I think we need to really stop there. Thank you for your attention.